Many of the techniques we've introduced for multi-electron atoms and for diatomic molecules can now be extended and generalized to provide information about the states of polyatomic molecules. So I want to present a little bit of an overview to get you acquainted and oriented with what this is all about. For the rest of this module, we'll be mostly sort of outlining different ways that we have of learning about the quantum states of polyatomic molecules. But I think this overview will be helpful in getting you situated so that you understand what it is we're talking about. All right, first of all, let's start with a Hamiltonian, which is written up here at the upper right. I've typed this out just because my handwriting doesn't always convey what it should, but I want you to look at each of these terms and be able to understand what they represent. For example, this very first term is the kinetic energy of the electrons. All right, so we're in atomic units, so we're not worrying about the mass of the electron. That's the unit of the atomic units. But it's just going to be the Laplacian over all of those electrons. So this summation here is over all the electrons in the molecule. So, whatever that molecule may be, if it's something like water, we've got 8 electrons on each oxygen, 6 on the carbon, so we would have a total of 22 electrons. So this would be a sum over 22 different electrons, ideally in this Hamiltonian. The next term is the attraction of those electrons to the nuclei. So in other words, this is the attractive force that holds those electrons on the atoms. So I'll simply note that it is a Coulomb attraction here, and it's one that we've seen before, although what we haven't seen as much before is the designation of the charge on the nucleus, which is given by Z. So you'll notice in these expressions I'm going to use I typically to indicate a count over electrons, and alpha and beta to indicate a count over nuclei. All right, this is followed by this term. It's a plus sign, so that means that this is a repulsive Coulomb term. And since we've got both I and J here, this is a repulsion between electrons. So this is once again electrons here in a repulsive interaction. Since electrons have a charge of 1, there's just a 1 in the numerator, not a Z. The next term, again, is positive, so it's a repulsive term, but now it's all indexed with nuclei, alpha and beta. So what we have here is basically the repulsion between two nuclei because they all have positive charges. We have to include that in the Hamiltonian. Finally, I have a term here that is basically the kinetic energy of the nuclei. And we include this for completion because the nuclei move around too, and they are also quantum mechanical objects. But this part here is what we've been defining, if you will, as the electronic Hamiltonian. And so that's the part that we're going to care most about, at least initially. And I'll note that it's this part that ultimately leads us to finding solutions for the electronic part of the wave function, which we can write as a function of the positions of all the electrons. This R is not just x, y, and z, it's x, y, and z for each of the electrons in the molecule. And these are parameterized by the locations of all the nuclei. So I'll just write it symbolically like this. I'll further note that these eigenstates for the electronic part of the Hamiltonian are each related to energies, and these energies are parameterized also by the positions of the nuclei. All right, once we solve this electronic part of the Hamiltonian, under the Born-Oppenheimer approximation, we can write that the total wave function is going to be the electronic part times a nuclear part. So I'll write that out over here. And these electronic energy levels are what's going to give rise to the potential surface on which the nuclei move. Right, we'll have a little bit more to say about that as this lesson proceeds. Okay, so our total wave function is this, but we're going to mostly be focused, at least initially, on the electronic part. Now, what we're going to be doing is using molecular orbital theory, and we've seen a taste of that in diatomics. We have an understanding that molecular orbitals are some kind of linear combination of atomic orbitals. And in fact, remember with the hydrogen atom, we defined our initial electronic orbital as a plus or minus of a 1s on one atom plus or minus 1s on the other atom. And so this is a fairly simple, maybe the simplest way, molecular orbital that one could construct. So we're going to be constructing similar sorts of molecular orbitals, but now generalizing this to all kinds of different orbitals, as we did in some of the higher atoms that form diatomic molecules. Okay, I don't want to necessarily limit it, though, to 2 atoms, because we'll find that in practice, molecular orbitals can extend over many atoms. So what I'm going to do is simply define, in general, a molecular orbital state, and I'll say this orbital state will be indexed by, some number k. We might also index it by what kinds of orbitals it connects, because those are usually related to each other in some way. And so we're going to be summing over all of the different atoms in the molecule. So this sum over the atoms, I've been using alpha up here, and I've already used my alpha here, so let's just say that this is the sum over the atoms I. And each of those atoms has atomic orbitals for this particular type of molecular orbital, so I'll put that label there. And these are reference to this particular molecular orbital. I'm sorry, I'm making the notation a little complicated here, but I hope it'll simplify in just a moment. These are all weighted by coefficient C sub k. So here's the main thing to remember. These are atomic orbitals on each atom. They are added together in a weighted fashion, weighted by these coefficients, and they combine together in a particular way to make one molecular orbital. All right, so here K is an index for the molecular orbital. Alpha is an index for the type of orbital. I'll say type of atomic orbital that we're doing. And I is a sum over the atoms. All right, so we're going to sum these things over all of the atoms, presumably, and create to create a different molecular orbital. Now, how do we do this in practice? There's a very particular strategy involved in molecular orbital theory, at least in most executions of molecular orbital theory. The first step is we define a basis. And I'm going to say a basis of atomic orbitals. Now, this may seem very easy. We know what atomic orbitals are from hydrogen, but in fact it turns out that there are many different ways that one can express that basis and many different ways that one can represent it mathematically. And how we define that basis is going to be critically important to how good the results are that we get out. And we'll spend a lot of time, especially in this lesson, talking about how one goes about choosing that basis and what the different choices mean. All right, the second strategy is we're going to optimize the coefficients. Second part of the strategy is optimize the coefficients C sub k. And actually, I probably should have made that C sub I, because we're adding over all of these terms. Okay, there's C sub I for the kth molecular orbital. All right, but these coefficients are something that we're going to get from doing a Hartree-Fock calculation, for example, using these molecular orbitals. So we're optimizing the coefficients, and what that does is it creates our linear combination of atomic orbital molecular orbitals that will eventually be our solution for this problem. All right, and then finally, we would populate these molecular orbitals with electrons. And that creates an electronic configuration for this polyatomic molecule. Now, I've drawn a couple of other things over here to the right. First of these is that once we have optimized these coefficients, we now can use these to construct the electronic wave function using a Slater determinant. So this is just our old friend, the Slater determinant. And you should recognize that each term in this determinant is a spin orbital. The spin orbital features a spatial part, which is the orbitals that we've been talking about over here, and a spin part, which we'll talk less about, but it follows all the same rules that we have seen for both multi-electronic atoms and diatomic molecules. All right, we're going to include all of the orbitals. Now, since we have, say, n electrons, that's our assumption, n electrons in this molecule, we're going to have a total of n over 2 orbitals that we typically can fill. So I've made some assumptions here in filling out this this Slater determinant. But you'll note that it sums over all the possible spin orbitals that I could have, for example, for electron 1. It can be in orbital 1 with spin alpha. It can be orbital 1 with spin beta, which would be the next term over here, all the way over to orbital n over 2 spin beta. Then we go down. Each row is an electron in the molecule. And so the lowest end of the first column would be orbital 1, but for electron n. And it goes across for orbital n over 2, spin beta for electron n. So using that example again, if we had 22 electrons in this would be a 22 by 22 determinant. And that's what represents the wave function for this molecule. Now, once we've populated the MOs with electrons, we can then go about calculating what the energy might be for this system. And it will be essentially this expectation value of the Hamiltonian. And I should have made this the electronic Hamiltonian, because that's really what we're dealing with here, is all the electronic parts of the problem. But that would give us the energy, and for a given nuclear configuration, it gives us the energy at that position of the nuclear of the atoms in the molecule. All right, so how would we proceed in practice? Okay, some of the approaches that are commonly used to solve these kinds of problems. Okay, so this is more of a module overview, because we're going to be looking at some of these different things. Well, one of the approaches that's used is to solve this electronic problem in a fashion that's called ab initio. So I'll call that the ab initio electronic, basically electronic state. Ab initio is just a word that means from the beginning. In other words, we're not making any assumptions. We're simply using what we know about the physics, the fundamental Hamiltonian for the system, and solving it the best we can using the tools that are available. Mostly what this will mean for us is the Hartree-Fock self-consistent field method, although we'll talk a little bit about some other methods that go beyond the Hartree-Fock method. I should note that these problems you will not be asked to solve with pencil and paper. All of these are problems for polyatomic molecules that we have very elaborate computer programs, maybe the most famous of which is Gaussian. Spartan is another one that I know we have a license for here. So these are programs that can be used to actually solve this problem. You need to give it certain input, but it can solve these problems. All right, when the Hartree-Fock method is not enough, we can extend beyond Hartree-Fock. But usually the first step is the Hartree-Fock self-consistent field result. All right, and programs are also available to handle that as well. Some of these extensions include things like something called configuration interaction, which is a way of mixing several different possible configurations in the molecular orbitals together. Another way is to use perturbation theory to extend the Hartree-Fock methods. All right, and I'm not going to go into great detail on the math of this. What I want you to be aware of is that Hartree-Fock is a great starting point, but if we want better results, sometimes we need to go beyond Hartree-Fock to these other sorts of things. Now, another approach that one might use if one is okay with less accurate results, but perhaps some deeper understanding about the chemistry and physics of these, is to incorporate some known data as we formulate our quantum mechanical problem. All right, now this shortcuts the calculation, so it's a lot easier to calculate. And some of these actually can even be done by hand. But one has to realize that what one is sacrificing here is you're not going to get quantitative results for energy levels and eigenstates, but you may get some deeper understanding about what those states mean. This is an approach called semi-empirical. Okay, it is empirical in the sense that we use information from experiment or use information from other calculations as input to shortcut our calculational process, but we still carry out a quantum mechanical calculation. Another way that one approaches some of the problems in polyatomic molecules is to simply use mathematical functions to represent the coordinate dependence of these eigenvalues. All right, so in other words, we're just going to say, you know, this thing vibrates like a harmonic oscillator. I'm going to use a harmonic oscillator to represent the nuclear motion. All right, this is an approach called empirical. In other words, we're not really using any sort of ground level or quantum mechanics to solve these problems. We're simply going to make a guess, and we're going to use experimental information to refine our guess so that the functions that we're using are actually reasonably realistic. One of the great sets of functions used for this is something called molecular mechanics. Another great tool for this is a program called CHARM, which is developed at Harvard for studying macromolecules like proteins and so forth. All right. There are many other powerful methods for studying polyatomic molecules. We're just scratching the surface here. I want to give you a little bit of a flavor for how this works, and that this is really a difficult problem. These are very sophisticated systems with many moving parts. I mean, just looking at the Hamiltonian tells us there's a lot going on in polyatomic molecules, but there's also a lot we can learn if we're a little bit clever about how we pose the problem and about how we go about solving it.